Welcome students to the second lecture on infinite series. If you remember, in the first lecture we were looking at binomial expansions of expressions such as 1 minus r whole to the power minus 1, which is equal to 1 plus r square plus r cube, that is sigma r to the power I is equal to 0 to infinity, and this is valid for modulus of r less than 1. Also, we have seen that 1 plus r whole to the power minus 1 is equal to 1 minus r plus r square minus r cube plus this infinite series, which is equal to sigma minus r to the power I is equal to 0 to infinity. Again, modulus of r is less than 1. Today, we will start with some simple problem to verify these expressions. Okay? So, problem 1, what is 0.8 minus 1? We all know that 0.8 is equal to 8 by 10, and its minus 1 means we are looking at 10 by 8, which we all of us know that is 1.25. So, in this case we know the answer. So, what I like to show is that can we get the same answer by expanding it infinite. So, our question is, can we get the same answer by expanding its infinite sum? How to do that? So, we look at it in the following way. We know (0.8) inverse is equal to 1 minus 0.2 minus 1. So, this comes of the form 1 minus r whole to the power minus 1, where modulus of r is less than 1, since 0.2 modulus is less than 1. So, this condition is satisfied. Therefore, we can expand it with the series expansion that we have seen at the beginning. So, let us try whether it holds good or not. Therefore, by the series expansion, this is 1 plus 0.2 square, 0.2 plus 0.2 square plus 0.2 cube plus this infinite sum. If we consider this part, we have already got 1.2, but we know the answer is 1.25. So, our target is to show whether this sum is equal to 0.05 or not. So, what is this sum? This sum is 0.2 square plus 0.2 cube plus 0.2 whole to the power 4 plus this infinite sum, which is equal to, if we take out 0.2 square common, 1 plus 0.2 plus 0.2 square, and this is a GP series. Therefore, this is equal to 0.2 square, and we know that this sum is 1 minus r to the power n upon 1 minus r, which is equal to 0.2 square, 0.2 square multiplied by 1 minus 0.2 whole to the power n upon 1 minus 0.2, and take limit n goes to infinity. Therefore, this becomes 0.2 square multiplied by 1 upon 1 minus 0.2 is equal to 0.2 square into 1 upon 0.8, which is equal to 0.04 upon 0.8 equal to 1 upon 20, which is equal to 0.05. Therefore, the whole sum is 1.2 plus 0.05 equal to 1.25, and we know that that is the right answer. So, this example suggests that we can get the right answer by expanding the binomial series the way we have done. 1 minus r whole to the power minus 1 is equal to 1 plus r square plus r cube up to infinity. Let us take a very similar problem. Problem number 2. What is 1 plus 0.2 to the power minus 1? We know the answer. We know the answer because this is 1.2 inverse is equal to 12 upon 10 inverse, which is equal to 10 upon 12, which is equal to 5 upon 6, which is equal to 0.8333 like that. Okay. So, we know the answer. We shall have to see whether we get the same answer by expanding it as a series. We have the formula 1 plus r whole to the power minus 1 is equal to 1 minus r plus r square minus r cube, etc. Therefore, 1 plus 0.2 inverse is 1 minus 0.2 plus 0.2 square minus 0.2 cube plus, like that. We have already got here 0.8. Therefore, what needs to be checked is whether this is going to be 0.033. All right. So, this is what we need to check, and like the previous problem, we can look at it as a geometric series. It is 0.2 whole square into 1 minus 0.2 plus 0.2 square minus, like that. So, this is the infinite series where common ratio is minus 0.2. Therefore, this sum is 0.04 multiplied by 1 upon 1 plus 0.2. This is 0.04 multiplied by 1 upon 1.2, which is equal to 4 upon 120, which is equal to 1 upon 30, which is equal to 0.0333. Therefore, the answer is 0.8333. Therefore, we see that for both 1 minus r whole to the power minus 1 and 1 plus r whole to the power minus 1, we can verify that the series actually gives the right answer when we check it with some known values. Note that so far we have not really proved it, but we have just verified. Now, the question is it true for only minus 1? Can we have similar expansion, say for minus 2, minus 3, or what about some rational number say half, 2 by 3? That is the question. In short, we have earlier studied binomial theorem. For positive integer n, and we know that 1 plus x whole to the power n is equal to 1 plus n c 1 x plus n c 2 x square plus n x to the power n minus 1 plus x to the power n. So, the characteristic that we had for positive integral index n is that number of terms is finite, B, we could use combination n C r for r is equal to 0, 1 up to n. We could do these things. The problem with negative integral, negative index is 1, the number of terms is infinite, but more importantly, we cannot use minus n C r as this is not defined. Therefore, we have to do things in a slightly different way. But before that, let us first see what is 1 minus r whole to the power minus 2. Again, we assume that we can write it as a polynomial in R, which will be convergent for modulus of R less than 1. Our aim is to find out the coefficients of the expansion. Right? If this is not infinite, if this is finite, then what will happen? Then after certain n, the corresponding coefficients will become 0. So, let us target to find out the coefficients of 1 minus r whole to the power minus 2. Let us assume one minus r whole to the power minus 2 is equal to a 0 plus a 1 r plus a 2 r square, like that. Okay? Our aim is to find these coefficients. We know that 1 minus r whole to the power minus 2 is equal to 1 minus r whole to the power minus 1 multiplied by 1 minus r to the power minus 1. Therefore, we can write this as the product of the corresponding series, which is equal to 1 plus r square plus multiplied by 1 plus r square plus. Then what we will try to do? We will try to find out coefficients of r to the power k for different powers of k, and then we will try to compare a0, a1, a2 with those values. So, let us write it again. 1 plus r square plus multiplied by 1 plus r square. Therefore, coefficient of r to the power 0, we can see that the only term that does not involve any r is product of this into this is equal to 1. Therefore, a0 is equal to 1. Coefficient of r is equal to, we can get r in two ways. This one multiplied with this r and this r multiplied with this one. Therefore, coefficient of r is equal to 1 plus 1 is equal to 2. Therefore, a1 is equal to 2. What is coefficient of r square? We can find r square in three different ways. We can compute r square in three different ways. 1 into r square plus r into r plus r square into 1, because other terms are higher powers of r, none of them will contribute to r square. Therefore, coefficient of r square is 1 plus 1 plus 1 is equal to 3. Therefore, a2 is equal to 3. Let me go for one more term that will make you understand the pattern. Coefficient of r cube. In a similar way, 1 plus r cube, r into r square into r, and then r cube into 1, all four of them will give r cube. Therefore, coefficient of r cube is equal to 4. Therefore, a3 is equal to 4. In general, coefficient of r to the power k is equal to k plus 1, right? Because there will be k plus 1 terms, 1, r square up to r to the power k. Each one of them, when multiplied with one particular term here, will give you r to the power k. Therefore, we can write (1 minus r whole to the power minus 2) is equal to 1 plus 2r plus 3r square plus 4r cube. Like that, we can get an infinite sum for the expression 1 minus r whole to the power minus 2. From here, we can easily see that 1 plus r whole to the power minus 2 is equal to 1 minus r whole to the power minus 2. Therefore, this is going to be 1 minus 2 r plus 3 r square minus 4 r cube. That I suggest that you expand 1 plus r whole to the power minus 2 as the product of 1 plus r to the power minus 1 into 1 plus r whole to the power minus 1, and then try to match the coefficients and try to obtain this as the expression for 1 plus r whole to the power minus 2. Let me go to the next problem. What is 1 minus r whole to the power minus 3? Again, as before, we assume 1 minus r whole to the power minus 3 is equal to that infinite series b 0 plus b 1 r plus b 2 r square plus b 3 r cube plus this infinite sum, and we try to find the values of b 0, b 1, b 2, etc. How to do that? We will do that in the following way. We will write (1 minus r whole to the power minus 3) is equal to 1 minus r to the power minus 2 into 1 minus r to the power minus 1. We already know the series expansion for this. We already know the series expansion for this. Therefore, the way we have done for 1 minus r whole to the power minus 2, we will try to do in a similar way for 1 minus r whole to the power minus 3. And 1 minus r to the power minus 2 multiplied by 1 minus r to the power minus 1 is equal to 1 plus 2 r plus 3 r square plus 4 r cube, like that, multiplied by 1 plus r plus r square. So, in the product, coefficient of r to the power 0 is equal to 1 multiplied by 1 is equal to 1. Therefore, b 0 is equal to 1. Coefficient of r is equal to 1 times this r plus 2 r times 1. Can you see that? This one multiplied with r will give 1 r, and these 2 r multiplied with this one will give 2 r's. So, this is 1 plus 2 whole to the power 1 plus 2. Therefore, b 1 is equal to 3. coefficient of r square. Now, you can easily find out this one multiplied by this r square will give me 1 plus these 2 r multiplied with this r will give me 2 r square plus this 3 r square multiplied with this 1 will give me 3 r square. Therefore, it is 6. Therefore, B 2 is equal to 6. I will go for one more term, coefficient of r cube is equal to 1 multiplied by r cube, that is 1, plus 2 r multiplied by r square, that is 2, plus 3 r multiplied by r, that is 3, plus 4 r multiplied by 1, 4 r cube multiplied by 1, that is 4, is equal to 10. Therefore, B 3 is equal to 10. So, this gives us an idea of the series Therefore, what is going to be the general term? Is 1 multiplied by k plus 1 plus 1 multiplied by k plus 1 multiplied by k minus 1 up to 1 multiplied with 1, which is equal to 1 multiplied by 1 plus 2 plus 3 up to k plus 1, which is equal to k plus 1 into k plus 2 by 2. This is going to be B k is equal to coefficient of r to the power k. So, you look at it, when r is equal to 0, it is 1 into 2 by 2, this is 1. When k is equal to 1, it is 2 plus 3 by 2 is equal to 3. When k is equal to 2, it is 3 plus 4, 3 multiplied by 4, which is 12 divided by 2 is equal to 6. When k is equal to 3, it is 4 multiplied by 5 is equal to 20 divided by 2 is equal to 10. Therefore, we get an expression for 1 minus r whole to the power minus 3 as follows. 1 minus r whole to the power minus 3 is therefore sigma k is equal to 0 to infinity k plus 1 into k plus 2 by 2 r to the power k. Obviously, it is not possible to compute these terms for arbitrarily large n. We need to derive a formula. What is that? For positive n, for positive integral n, we have coefficient of r to the power k is equal to n c k. We have already seen that such terms are not valid for negative n. What we do? We write NCR as factorial n upon factorial r into factorial n minus r is equal to. We can now cancel few terms from n factorial and n minus r factorial. So, what we get is n into n minus 1 up to n minus r minus 1 divided by r factorial. So, this gives us the formula. So, let us denote by c minus n k the term minus n into minus n minus 1 into minus n minus 2 up to minus n minus k plus 1 divided by k factorial. We shall see that c minus n comma k is the coefficient of r to the power k in the expansion of 1 plus x whole to the power minus n, where modulus of x is less than 1. Verification. Consider 1 minus r whole to the power minus 2, coefficient of r is equal to minus 2 upon 1 factorial is equal to coefficient of minus r is equal to minus 2 1 factorial is equal to minus 2, coefficient of minus r square is equal to minus 2 minus 3 upon 2 factorial, which is equal to 3, coefficient of minus r cube is equal to minus 2 minus 3 minus 4 upon factorial 3, which is equal to 4, like that. Minus 2 minus 3 minus 4 upon factorial 3, which is equal to minus 4, like that. Therefore, the expansion is one plus minus 2 into minus r plus 3 into minus r whole square plus minus 4 into minus r whole cube, like that, is equal to 1 plus 2r plus 3r square plus 4r cube, or we see that this is the series that we have got when we have made the algebraic manipulation. So, this is one verification of the result that I have just stated. Let us verify for 1 plus r whole to the power minus 3, coef of r is equal to minus 3 upon 1 factorial, which is equal to minus 3. Coefficient of r square is equal to minus 3 into minus 4 upon 2 factorial, which is equal to plus 6. Coefficient of r cube is equal to minus 3 minus 4 minus 5 upon factorial 3, which is equal to minus 10, like that. Therefore, we can see that 1 plus r whole to the power minus 3 is equal to 1 minus 3r plus 6r square minus 10r cube, and we have seen the similar result for 1 minus r whole to the power minus 3. Putting r in place of minus r, we will get this result. Next, we shall look into binomial expansion with fractional index. That is, what is 1 minus x whole to the power half, or 1 minus x whole to the power minus half. Let us try. Consider 1 minus x whole to the power minus half. We know that one minus x whole to the power minus 1 is equal to 1 minus x whole to the power minus half into 1 minus x whole to the power minus half. This is equal to 1 plus x square plus x cube for modulus of x less than 1. Let us assume one minus x whole to the power minus half is equal to a0 plus a1 x plus a2 x square, like that. Then we can multiply this by itself, and if we equate the coefficients with 1 plus x square plus x cube with this series, then we will get different equations, and from there we will try to solve these values for a0, a1, a2, etc. So, we have is equal to a0 plus a1 x plus a2 x square multiplied by a0 plus a1 x plus a2 x square. Let me write one more term for each. is equal to 1 plus x square plus x cube. Therefore, what we get? The constant is a0 square. And that we can equate with the constant of this series, which is 1. Therefore, a0 square is equal to 1. Therefore, a0 is equal to plus minus 1. But we take the positive side and see. Therefore, let us assume that a0 is equal to 1. What is the coefficient of x? It is a0 a1 plus a1 a0 is equal to 2 into a0 into a1 is equal to 2 a1, which is equal to 1. This comes from the series 1 minus x whole to the power minus 1. Therefore, 2 a1 is equal to 1. Therefore, a1 is equal to half. Coefficient of x square is equal to a0 into a2 plus a1 square plus a2 into a0 is equal to 1. Therefore, 2 a0 a2 plus a1 square is equal to 1. Therefore, 2 a0 a2 is equal to 1 minus 1 by 4 is equal to 3 by 4. Therefore, 2 a2 is equal to 3 by 4. Therefore, a2 is equal to 3 by 8. Therefore, we get that 1 minus x whole to the power minus half is equal to 1 plus half into x plus 3 by 8 into x square plus dot dot. We will see whether we get the same by using the expansion the way we did for negative integers. So, for negative integers what we did, if you remember, we have seen that coefficient of x to the power k in 1 minus x whole to the power minus n is equal to minus n minus 1 minus n minus k plus 1 upon factorial k. Let us apply the same for p by q. In particular, here for minus half. Therefore, by using similar expansion, we get 1 minus x whole to the power minus half is equal to 1 minus half into x plus minus half into minus half minus 1 upon factorial 2 square etc. is equal to 1 plus half x plus 3 by 8 x square, and we have already obtained that a 0 is equal to 1, a 1 is equal to half, a 2 is equal to 3 by 8. Thus, we get the same answer. Okay, friends, with that I stop this session. In the next session, I shall expand more with these formulae. Thank you.